Hello, everyone. My name is Chen from ETH Zurich. Today, I'm going to present cTPM, a cloud TPM for cross-device trusted applications. This is a joint work with Himanshu, Stefan, Saroiu, and Alec Wolman from Microsoft Research. This work is done during my last summer internship at Microsoft Research. To motivate our work, today, people are increasingly using more than one mobile device. Sharing information across multiple devices has greatly boosted user experiences. As another trend for mobile computing world, mobile devices have started to use trusted hardware. One important such trusted hardware is Trusted Platform Module, or TPM for short. For example, Google Chromebooks are using TPMs for many features like firmware rollback prevention and file encryption. And Windows 8 is using TPMs for applications like BitLocker and virtual smart cards. There are also many research prototypes proposed by the research community. Among them are Pasture, which offers secure offline data access, trusted sensors, which use TPMs to sign the sensor readings, and trusted language runtime, which build a .NET language runtime for building trusted applications. We further notice that cross-device data sharing is easy. Today, most mobile applications implement some form of app state or data sharing across multiple devices. However, for these trusted applications whose data, state, and crypto keys are usually protected by the trusted hardware like TPM, sharing the TPM-protected data becomes hard. The primary reason for this difficulty is because the keys managed and protected by the TPM are by TPM design bound to the TPM chip. Let me use this animation to illustrate why this is the case. In the beginning, a set of root keys are installed by the TPM manufacturers before the TPM chip are shipped to the customers. After that, these root keys are guaranteed never leave the TPM chip. And then the keys generated by the TPM and will be used by the applications are either in the TPM chip or protected by these root keys when they are outside of TPM chip. As a result, as long as these root keys never leave TPM chip, these keys generated by the TPM chip will be secrets only known to the TPM chip itself. Current TPM specification did provide mechanisms to migrate key from one TPM to another. However, to use it, a PKI from a third party has to be provisioned, and configuration of this key migration has to be conducted in a malware-free environment. Both of these two requirements are hard to achieve on mobile devices. I will come back to this point in 2 minutes. So the main research question in this work is, what is the minimal change we can make to the TPM design to enable sharing of TPM-protected data? Our answer to this question is cTPM, which is short for Cloud TPM. As indicated by the name, a cTPM is a TPM chip that can use cloud services to provide extra features, including this key migration. Compared to TPM design, the primary change we make to this TPM chip is to require additional root keys pre-shared with the cloud. Let me give you a flavor about how these shared root keys can help sharing data across TPMs. Let's assume two cTPM running on two mobile devices belong to the same user. And the cloud runs two TPM emulators for the user. And these two TPM emulators will be bound to the same user. And there is a set of root keys shared between each pair of cTPM device and the TPM emulator running in the cloud. With these shared root keys, we can enable secure communication channel between each pair of cTPM device and the TPM emulator. With the established secure communication channel and the help of the cloud, now sharing TPM-protected data becomes easy. What's more, in fact, with this established secure channel, the cloud could further provide 2 extra features to the cTPM chip. Today, TPM chip usually has a small and slow persistent storage device called non-volatile RAM, or NVRAM for short. Each slot in this NVRAM also only tolerates around 10,000 writes during its entire lifetime. With this established secure channel, the first feature that the cloud could provide for cTPM chip is a fast and large remote NVRAM storage. As for the second feature, current TPM chip only has a trusted timer. It doesn't have a trusted clock. Therefore, policies like this movie can only be watched after midnight Friday cannot be implemented. With this established secure channel, now the cTPM chip can maintain a local clock and sync it with the clock in the cloud. And therefore, these interesting time-relevant policies could be implemented. Here's the outline of my today's talk. After talking about our motivation, let me first talk about TPM as a background in case people are not familiar with it. And then I will talk about why design alternatives are not favorable. TPM, short for Trusted Platform Module, is a secure coprocessor offering multiple crypto primitives. It also enables measurement and attestation of code running in the platform. TPM chip is a vital component for trust computing technology and is already widely deployed in laptops produced by mainstream manufacturers like Lenovo and etc. Nowadays, Trust Computing Group defines specification for TPM chip. The current completed specification is TPM 1.2. It is widely deployed in the commodity chip in the laptops. However, there is one emerging TPM specification, TPM 2.0, which is used to replace TPM 1.2. Our cTPM is based on TPM 2.0. But I want to point out that our cTPM design does not rely on any feature specific to TPM 2.0. It could be easily ported to TPM 1.2. For the trust model, threat model, we also adopt the same threat model as the current TPM chip. In other words, all sorts of software-based attacks, including malware, will be considered in our threat model. However, we don't consider physical attacks such as microscoping the TPM chip and read out root keys. For trust assumptions, our cTPM design keeps a dual relationship with the cloud. On one hand, it trusts the shared root keys with the cloud. It trusts the cloud for the shared root keys, and all the keys derive from these shared root keys. However, it keeps all the root keys in current TPM design local to the chip and isolate them from the other shared keys. As a result, even if the cloud is compromised, only the keys shared with the cloud will be compromised. The keys that are local to the TPM chip will still be secure. And finally, securing cloud services without trusting the cloud has been an active research area. We leave the work to secure the cloud side of cTPM as our future work. For now, let's assume that we can trust the cloud not to leak the shared keys. As a design alternative, secure execution mode could be used as a TPM extensibility mechanism. This mode is also called Trusted Execution Technology by Intel. It implements a CPU-based reboot to run trusted code in an isolated environment. It could generally be used to implement additional TPM functionality, such as this key migration across TPMs. In order to remove operating system out of the trust computing base, we can usually run secure execution mode in 2 steps. In the first step, we first suspend the operating system initiate this secure execution mode, and then run this additional TPM code. In the second step, after the code is finished, we do necessary cleanup, exit secure execution mode, and then resume operating system. Even though the logic here may seem simple, it is actually very challenging for mobile devices to use secure execution mode in this way. First, it poses performance issues, as all the code, including operating system and other applications, will be suspended. No progress can be made on the platform before the TPM code is finished. Also, as the operating system is suspended, the TPM code is running like on a bare metal. This poses engineering issues for the code developer. In fact, today, there are no ARM processors supporting this secure execution mode, which prevents mobile devices from using this code from the beginning. Finally, as a proof of these challenges, today, there is no software production code using secure execution mode in this way. After briefly talking about why secure execution mode is not favorable as a design alternative, let me introduce cTPM design and implementation details. In this work, we will mainly address these 5 design challenges. First, what are these root keys shared with the cloud, and how do we provision them? Second, with these root keys, how do we design secure key sharing across cTPMs? We will see this requires a secure communication channel. And next, I will talk about details of this secure communication channel. Finally, with this secure communication channel, I will briefly talk about how we design cloud-side NV storage and trusted clock. So the additional pre-shared root keys are cTPM's root of trust. cTPM generates these root keys using a random seed pre-shared with the cloud. We can think of this random seed as, in the future, iPhone and iPads can share this random seed with iCloud, and Microsoft Surfaces can share a random seed with Microsoft Azure. And on each boot up with this random seed, cTPM will generate 2 root keys in deterministic way. The first one is called Cloud Root Key, or CRK. It is used to protect the secrets shared across cTPMs and with the cloud. The second key is called Cloud Communication Key, or CCK. It is used to protect the data exchange between cTPM and cloud and establish the secure communication channel. Now let's see how to share keys in our cTPM design. Cloud root key plays a significant role here. Again, let's suppose 2 cTPMs running on 2 mobile devices belonging to the same user, and the user wants to share keys across its cTPM device. In cTPM, this is done in 3 steps with the help of 2 TPM emulators in the cloud. In the first step, the user asks the cloud to generate a shared key, and the cloud will use command TPM to create a shared key between its TPM emulators. The key output by this command will be protected by the cloud root key of each TPM emulator. And in the second step, the cloud can ship the shared key to each of the cTPM device using this secure communication channel. And finally, each cTPM device can simply use TPM to load the key into TPM's memory and obtain a handle for later use. At a high level, we can see through these 3 steps, the cTPM device only executes one simple command to load a shared key. Neither secure execution mode nor PKI from a third party has to be provisioned. The only missing component here is this secure communication channel between the cTPM device and the cloud. So let's talk about details of this secure communication channel. In cTPM, we use cloud-side NVRAM as a message box for the cTPM device and cloud to communicate with each other. In general, sending and receiving messages by cTPM is like NV write and NV read to this remote cloud-side NVRAM. Also, as transient network connectivity loss is common on mobile devices, we also provide cache on cTPM side to mask this transient network connectivity loss. We provide synchronization protocols to sync the client-side cache and cloud-side persistent storage. Here are some details of our synchronization protocols. We design a pull and a push method for NV read and NV write. Each of this synchronization process involves two messages switched between cTPM and the cloud. Here I only want to highlight two details about our synchronization protocol. First, the messages switched between cTPM and the cloud will be protected by this cloud communication key. Second, nonce and counter are used to prevent message replay by the software stacks on the mobile devices and the network node in the middle between cTPM and cloud. I further want to point out that in each of the synchronization protocols, it is the cTPM device who initiates the connection with the cloud. However, in current TPM usage model, TPM is supposed to handle commands and return result. It cannot initiate the connection with the cloud required by this synchronization protocol. So there is a problem. To solve this problem, we propose a method called secure asynchronous communication. In this method, the caller app assumes the position of a connection initiator and a message forwarder. The method divides each synchronization process into three phases. And let me use an example to explain this secure asynchronous communication. Suppose that the client would like to sync NV index 42 with the cloud. In the first phase, the caller app will send a command TPM to sync begin to cTPM to initiate this synchronization process and receive a blob from cTPM. In the second phase, the caller app can send this blob to the cloud. Cloud will use TPM to sync proc to process this blob and return a response blob prime. And in the final phase, the caller app can forward this blob prime to cTPM using TPM to sync end and obtain a result for this whole process. One observation of this synchronization process is in phase 1 and phase 3, whose latency are usually short. cTPM will be blocked and commands from other caller applications will not be handled. However, in phase 2, whose latency is dominated by network latency and potentially could be very long, cTPM can continue to handle commands from other caller applications. This helps cTPM to improve availability and responsiveness for other caller applications. And further, I want to remind you that here cTPM and the cloud are trusted, but the caller app are not trusted. With this method, we actually build a secure communication channel with the help of untrusted entities. With this established secure communication channel between cTPM and cloud, let's talk about our cloud-backed NV storage design and trusted clock. So local cached NV entries will have TTL values. If the TTL expires, the local cached NV entries is no longer available. And the caller app has to resync this local cached entry with the cloud-side persistent storage. Also, cTPM has a timeout to abort this cloud command. This timeout value could be adjusted by the cloud according to its needs. The current default value for this timeout is 5 minutes. Finally, with this remote NV storage enabled, providing a trusted clock is straightforward. the cloud can simply reserve a special TPM remote NV index and put the clock information into this remote NV index. The cTPM client can just read the information outside of this special NV index and even build policies upon this remote NV index. The only difference between this special remote NV index and the common normal remote index is that it uses a separate timeout value. And the default value for this timeout is 1 second to keep high precision of this trusted clock. For implementation details, in total, cTPM adds 3 new commands out of 108 commands in current TPM 2.0 specification. I have already covered the usage of these 3 commands in previous slides. Our cTPM is implemented based on TPM 2.0 reference implementation. This involves adding 1,300 lines of code out of 23,000. Finally, to prove the usefulness of cTPM, we re-implement Pasture and TrInc and make them work with cTPM. For Pasture, cTPM enables Pasture to support secure offline data access on multiple devices. And for TrInc, cTPM provides TrInc with high-performance NVRAM storage. After talking about our basic cTPM design and implementations, now I would like to share some evaluation results. Our evaluation testbed uses a client-side machine equipped with a TPM chip running cTPM client-side code. We also set up a server running the TPM emulator in virtual machine as the cloud service. We use wide area network emulator to emulate the communication channel between cTPM client and the cloud. And we use this emulator to emulate both Wi-Fi and 3G networks. We adopt the value of round-trip time from a report by Huang in Mobisys 2012. Specifically, we would like to answer 2 questions. First, are the cTPM protocols proposed secure? Second, what is the performance of crypto operations of cTPM compared with TPM chip? To answer the first question, we verify the correctness of our synchronization protocols with verifier ProVerif. We model an attacker with unrestricted access to operating system, application, and the network. I want to point out that the verification is upon a model of our synchronization protocols. We did not verify the implementation of our protocol. To answer the second question, we use experiment to compare the crypto operation performance between cTPM and the TPM chip. In the experiment, we create a 2048-bit RSA keys on both the TPM chip and the cloud-side TPM emulator, and we compare the latency of each round of this key creation. In the figure shows in the bottom, x-axis depicts the number of the round of key creation, and y-axis shows the latency of each round. The result shows that creating a 2048-bit RSA key on cTPM emulator is at least 12 times faster than that of a TPM chip, and the variation of key creation is also smaller. The primary reason for this is the crypto computation and entropy source in our cTPM software-based emulator are much faster than that of a TPM chip. We can envision this gap to be even larger when the cloud tries to implement TPM emulators using faster entropy source and high-performance crypto modules. To summarize, in this work, we present cTPM, which is essentially a TPM chip plus a random shared seed with the cloud. And we have demonstrated that this small change could support easy sharing of TPM-protected data for trusted applications. Further, this design change also enables 2 additional features. They are high-performance NV storage and trusted clock. Finally, we present a full implementation of cTPM based on TPM 2.0 specification. We also re-implement Pasture and TrInc on top of cTPM and extend their functionalities. With that, I will end my talk. I would like to answer your questions. Thank you.
Hi. So I'm suspicious. So I'm not a security person. I feel if I was a security person, I would be even more suspicious. But I feel like with TPMs, I can trust one physical chip that's on my computer. I know that the keys were embedded in there. That's a very trustworthy thing. And now we're moving to a scenario where we've got data that's sort of spreading across multiple machines. So not only do I no longer know that it's linked to one specific chip, but I'm also running these virtual TPMs in the cloud where that's sort of a whole other issue of I don't necessarily trust that at all. So what do you say about whether this is this still a TPM or is this something different that maybe still provides you other useful features?
Okay, good question. So I want to point out that our cTPM design keeps a dual relationship with the cloud. So on one hand, it trusts the root keys shared with the cloud, and it also isolates the keys local to TPM from these shared keys. Therefore, even if the cloud is compromised, the keys local to cTPM are still secure. If a user chooses to only trust its local TPM chip, it can use all the TPM functionalities currently available. However, if it wants to use services provided by the cloud, such as this easy key sharing or this NV storage provided by the cloud, it has somehow trust the cloud in this work. However, so securing this cloud service without trusting the cloud has been an active research area. We hope that this emerging technology, like Intel SGX, will help to protect the cloud-side cTPM and protect the secrets it shared with the cloud. Thank you.